Good morning, everyone. Happy Monday. How is everyone doing this fine week? Sorry that I'm a few minutes late today. Trying to get ready for you guys, and I'm just running a few minutes behind. That's good. Well, yeah, I know. I'm so excited for the sun. Oh my God. Can't wait to go for a walk today, Chloe. Okay, I think that is most of us just joining in. I have received a couple emails. Sorry, it's been a really busy weekend for me. I had my wine training, WSET2. So yeah, very busy on Saturday, Sunday. So I didn't get around to answering emails last night. And I was busy being a student again for a couple days. So I have dove into that realm to remind myself how annoying it is to study for things. So I feel your pain here for at least for a couple of days anyway. The exam went really well, which is great. So hopefully I've passed that WSET2, which would be great. But I noticed this morning that I had a couple emails about the Base 5 video assignment. So a couple of people just letting me know that they're having some issues with submitting. So let's take a little peek at the Dropbox. I just want to make sure that the Dropbox is at kind of maximum. So at least some of you have been able to submit. So that looks good. Oh, thanks, Ryan. Yeah, I got the old summertime hairdo cut last week. Let's just see. I know I've had this issue before, and usually it's with people that have Apple products, because for some reason Apple, when you're trying to convert stuff like into stuff that's going to be compatible with Windows, for example, Apple decides to make things very, very large and annoying to deal with. So I thought I had submission types. Yeah, so the upload limit is 100 megabytes. So anything that's over 100 megabytes, you're not going to be able to upload it as a file into our Dropbox. So what students usually find in this particular case, if you're unable to get the actual video into the Dropbox, then work on uploading your video to YouTube or some other kind of like our Dropbox, like anywhere where you can kind of post that video and host it, and someone with an invite, like even like Google Drive will probably also work if you have a Google Drive, and then you can just put the link. So just like open up a Word document, paste the link, and then upload the Word document to the actual Dropbox. I think that's probably the easiest for those of you that might be having some issues with uploading. So is Vincent on? Oh, yeah, so I know, Vincent, I know you would let me know you were having a couple issues, and Chris, Chris doesn't usually attend class, so I'll have to email him and let him know. But yeah, I think that's kind of the workaround. Normally I would accept these things as a USB, but we're not face-to-face. So yeah, the workaround I think is trying to upload it to like something like YouTube, Dropbox, Google Drive, and then just getting that linked to me somehow. Preferably inside the Dropbox, so I know that you've submitted something and I can mark it from inside the Dropbox. But if you email it to me, that's fine as well. So that's really all that we have on the docket today, right? I think this is still open until Wednesday. So even, for those of you that are still looking to, yeah, so you're still able to upload things until Wednesday. So no rush there. I'm certainly not going to be marking this because I still have your drafts to mark. I feel really bad because it's been a couple weekends, but I want to give good feedback for the drafts so that when you go to make your final product, you have that feedback. I've been able to kind of mark a few. I think I've marked about 5 of the submitted assignments. So it's a slow process. I'm sorry, I can't just sit down and do it in the span of a half an hour. So yeah, so just be patient with me. I'll try to get that done over the next couple of days. There's a lot that has kind of built up for me to do this week because of the wine training and because of the sale of my house here in Penticton and the move. So it's a little stressful for me. So I appreciate you guys having a little bit of patience. Yeah, so hopefully that'll work, Vincent. Hopefully that is the workaround for you. So try to, and let me know if it doesn't work, right? Like try uploading it to YouTube or something from your phone, see if that works. I think that's probably the easiest workaround. So just let it upload while you're watching a lecture or something, right? So your phone's not really doing anything else but uploading. Google Drive link, perfect. Yeah, that's awesome. Okay, so I think that's really all that's on the docket right now. I would like to kind of keep on trucking through our natural numbers section so that we can finish that up. I'm hoping to finish that up hopefully by Wednesday so that we can start kind of working, reminding ourselves about integers, models, and working with exponents. I wanted to do a little bit of work with like exponents and a little bit of work maybe with order of operations inside the integers section as well. So let's see, anyone else have any other kind of questions and or concerns? Yeah, sure. What's up, Wakana? You just let me know what's going on. Okay, so if Wakana does have some questions, she can post that in the chat for us. And in the meantime, we'll just do kind of a quick little recap. So, I see. When the numbers are really big, any tips on how to make a prime factorization? Yeah, there are a couple on that worksheet that I agree are a little bit tricky. So something like 871, let's see. So 871 not divisible by 3 or 9, right? Because it's 16 is the sum of the digits. So let's see, 871 is a toughie. We're going to maybe have to try to divide that by 7. That would be my first go-to, would be, try 7 and then try 13, and just use your calculator. So I look at the number something, I look at like 871 and I go, it's not even, it's not divisible by 3, it's not divisible by 9. So maybe it's divisible by 7. So 871, and I just did do this on my calculator. So it's not divisible by 7, and then I might try 13. 871 divided by 13. Okay, so I do get a divisibility by 13. So like I said, you try some of those other prime numbers that we haven't talked about, like 7 and 13. You can do that either by hand doing the long division algorithm or on your calculator. And when I do divide by 13, I get the number 67. So 67, yeah, exactly. So now that you have access to these prime numbers, right, with this little file that I posted up for you, you can start trying some of the prime numbers that don't have a divisibility rule, right? So looking at 871, for example, it's not even, it's not divisible by 3. We haven't tried 7, right? So, I tried 7, it didn't work, and then I just kind of keep going up. I know it's not divisible by 11 because it doesn't follow that alternating pattern. So then I tried 13 and I got the number 67. I know 67 is also prime, so 871 is 13 times 67, and that's the best we can do to decompose it. 754, that's 9 and 7, 6. So again, this is another number that's not divisible by 3 or 9, but it is an even number. So I might try dividing it by 4. So I'd probably go 754. Can it be divided by 4? No, but I can at least divide it by 2. So I could go 754 divided by 2, and I get 377. So, this is kind of my thought process. I get 2 times 377. I have no idea if 377 is prime without doing a little bit of a gut check on Google, I think. So 377 not divisible by 3 because the sum of the digits is 17. So that's not going to work. It's not even. So, I mean, we could try dividing it by 7. I wouldn't go much high, like I wouldn't go much higher than 17, really. So if we go 377 and we divide by 7, that doesn't work. 377 divided by 13 is 29. Okay, so that's kind of the trick here. So now I can go, oh, okay, well, this number 754 is 2 times 13 times, and I know 29 is prime because it's on my chart here. So that's usually how I try to tackle some of these awkward numbers. If you don't know, right, like let's say you get 377, you can always check using Google too, right? Google is a really good resource for you. So I mean, you just like, is 377 prime? Question mark. No, Google's very good at returning the answer quickly to you. Right, so that means we have to kind of search for a prime number that will divide into the number 377. So yeah, just, I mean, if you're unsure, you can always ask Google. It's a very quick search, and Google will return back it will almost be mean to you. Do you, do you hear Google laughing at us for asking it if 377 is prime? That's what it kind of feels like. It's not even nice about it, right? It's just like, no. Right? Like, at least you could be like, you could say something more than just no. Thanks, Google. But that's kind of the process that I try. I always try 2, 3, 9, 5, 11. I always kind of try those smaller numbers, and smaller prime. And yeah, please play again. Yeah, it's like rolling up the rim to win or something. So yeah, try those small prime numbers. If they don't work, then you try, don't go into your calculator, try dividing by 7, try dividing by 13, try dividing by 17. If none of those work, then go to Google and be like, is this number prime? And if it says yes, you have a 3-digit number that's a prime number. There's no easy way to know if it's prime after the number 100, because we don't really have a chart to refer to, unfortunately. So hopefully that is helpful. Most of the numbers that I'm going to be asking you to decompose, like on the final exam, for instance, will be numbers that follow a lot of those divisibility patterns that we talked about, like 3s and 11. I really like 3s and 11s. I like that patterning. I like 9s. Yeah, so I mean, working on a few more examples of prime power factorization. Hopefully those made sense. Is there anything that you wanted a little bit more elaboration on from those 2 examples at all? Okay, so we're going to combine 2 sections here into one, because I think we can probably blast through these topics relatively quickly. I feel like you guys have pretty good skills when it comes to working with numbers, which is a great thing to see. I want to talk about the lowest common multiple and the greatest common factor, just so that you have this for your notes in case this is something that you have to teach in middle school when we start talking about fractions. It's really nice to have an idea of what these things mean and have a really nice way to, I think, to describe this kind of stuff. So let's, I guess, just maybe try to unpack the terminology first. And one of the words that we've seen already is the word factor, right? So when we're thinking about a multiplication statement, a factor is one of those 2 pieces that get multiplied together to get our larger number. So we want to think about it from a division kind of standpoint, because we're going to probably be working with the larger numbers and trying to get factors of the larger number. So we could say that a factor essentially is a number that divides evenly into a composite number. And I should actually be a little bit careful. We're just going to go with any number. So a number that divides evenly into a number is called a factor. And maybe let's say another number. Right, so for example, we know that, I don't know, 3 times 7 is equal to 21. Right, thinking about this in terms of division, we know that 21 divided by 3 is equal to 7. And we know that 21 divided by 7 is equal to 3. So 3 and 7 divide evenly into the number 21. So 3 and 7 are both factors of the number 21. Okay, let's step back for a hot second. Every number has at least a factor. Hopefully you can get behind that. Every single number has at least one factor. What is that factor? What number always divides evenly into every single number? The number 1. So 1 is always a factor of every single number. Right, because we can always take a whole number and divide it evenly into one equal size group. We just get the original number back, right? So that's the idea here. Any number divided by 1, we know it's equal to 1. So this has something to do with that multiplication identity thing, right? If I take any number, like the number n, and I multiply it by 1, I get n. So we know that any number divided by the number 1 is also going to be equal to itself. So it has something to do with the identity, the multiplicative identity idea here. Right, so 1 always divides nice and evenly, which is a good thing. So let's consider two numbers. Let's maybe call them n and m. So we'll look at an example after where we actually have whole numbers. We're going to take two numbers. Now, what we could do is we could find all of the factors of n, find all of the factors of m, and then we could look at those lists and we could see if there are any shared factors on that list, right? So kind of looking at the intersection of those sets. Ryan had a question. So if we were trying to find the answer, we got 6.3. Yeah, so if you get a decimal number in your calculator, you know that it's not evenly divisible. So we can't really call it a factor in the context of this particular chapter that we're working with. Yeah, so if you get a decimal number, you know you can't evenly divide into something, in which case it's not going to be a factor. That is correct. Okay, so what I would like to define next is, now that we have a refresher of what a factor is, we want to think about what does common factor mean. So in order for us to talk about a common factor, we need two numbers and we need to have a list, a full list of all of the factors of these numbers. And we'll take a look at how to create that list in a moment. When I look at those two lists, if there are some shared factors, some shared numbers inside of these two lists, we're going to call those common factors. And for those of you that want to make some connections here, if we called like the first list set A and we called the second list set B, we're looking for the intersection of these two sets, the intersection of these lists. Okay, so let's maybe take some smaller numbers here. Let's see if we can find all of the factors of, let's say, 12, and let's take 16. I think 16 is a nice number here. So let's work on 12 first. Can you give me some factors of the number 12? So which numbers divide evenly into the number 12? Two and three will, yep. So 2 and 3 are definitely on this list. 2, 3, 6, yep, I believe with you. Believe with you, believe you. 1, yeah, don't forget the number 1, right? 1 is always a factor. Yep, we're missing the number 4. Nice catch, nice catch. And there's one more we need. So there's one more number that divides evenly into 12, and that is the number 12. Yeah, so every number, every number is also its own factor in some sense, right? Every number can be evenly divided. You know, if you make that many groups, you can always divide it and get one thing per group. So yeah, each number is always one of its own factors. I think this is the full list. Now I'm going to go ahead, I'm going to rewrite this in a bit more of a seductive way so that we can see a really interesting pattern that pops up here, okay? So those are all the 6 factors. Let's write them like this. 1 beside 12. I'm putting 1 beside 12 because I know 1 times 12 is equal to 12. Okay, next is 2 and 6 because 2 times 6 is equal to 12. So essentially I'm trying to arrange this in a way so that I kind of know that I have the full list. The last pair we had was 3 and 4, right? 3 times 4 is equal to 12. So I like to arrange my lists in a way so that I can kind of visually see that I have them all. I know that there aren't going to be any other factors because I start with the number 1, I move to the number 2, I move to the number 3. So there's no numbers in between 1 and 2 or 2 and 3, like no whole numbers. And then from 3, I go directly to the number 4. I'm on the other side now. And then the other side starts increasing, which I don't really care about. But there are no numbers in between 3 and 4. So I kind of know that this list is done based on the way that I've organized it here. I know I haven't missed any factors. So that's how I typically like to write down my lists. That's just a little aside for you guys. So if we do the same thing for the number 16, let's just write that one out quickly. So 1 times 16 is equal to 16. Then we go to the next number. The next number is 2. Does 2 times something equal 16? Yep, definitely. The number 8. Then we would go to the number 3. Does 3 times something equal 16? I don't think so, right? I don't think 3 is going to work. Then we go to the number 4. You know, does 4 times something equal 16? Yes, 4 times 4 equals 16. Whenever you, like, okay, so 4 times 4, and then I know I'm done because I've kind of hit the middle of my ordered list. So hopefully that makes sense why I like to kind of arrange things like this. When I have a similar factor, sometimes I like to just put that factor in the middle. That's a personal preference. If you want to write 4 and 4, that's fine with me too. We just have to be careful about when I go to talk about the number of factors. So if I look at 12, 12 has 6 factors, 1, 2, 3, 4, 6, and 12. If I look at the number 16, it has 5 factors: 1, 2, 4, 8, and 16. So if you were to write it like this, we just don't want to double count the number 4. We want to count 1, 2, 4, 8, and 16. Yeah, exactly. So if we think about this as sets, we just don't want to write down that number twice. It's kind of just semantics, right? I like putting it in the middle just to, I don't know, I guess be different or something, but it prevents me from accidentally writing down that 16 has 6 factors, that's all. Okay, so these are our sets. Is 1 a factor of 1? Yeah, exactly. 1 is a factor of 1. That's the only factor for the number 1. Yeah, exactly. So if I'm looking at the number 1 and I want to write down all of its factors, there it is as an ordered list. It's just itself. Yeah, you're right. It's not a prime number. We can't invite it to the prime party. Otherwise, we don't have a unique prime power factorization. That's the reason why it's not prime. And you're right, it is technically divisible by 1 and itself. So it technically satisfies that part of the definition of being a prime number. But yeah, it unfortunately gets excluded because it's the multiplicative identity, and we can keep multiplying by the number 1. And we don't have, yeah, we don't have a unique factorization anymore if we allow 1 to be prime. So it's a weird math thing. I mean, I'm not super chuffed that you know the ins and outs of why mathematicians like unique things, but that's the real reason. We just want to make sure that the factorization is unique, and it can't be unique if we include the number 1. That's all. Okay, 59 has no markings. Is it special in any way, or is it just a prime number? So 59, is it special? I mean, it's special because it's prime, right? So, oh, I see. I see what you mean. There should be a little star here. So yeah, if you want to make a little star here, 59 is definitely a prime number. I might have just, and same with 73. It looks like I forgot to put a little star by 73 as well. I will try to remember to update that for us on the page, on our Moodle page. Yeah, so 59 and 73 are both prime numbers because we didn't cross them off in any way. And hopefully this is a little bit easier of a way to kind of visualize the prime numbers. Hey, yeah, no worries. Thanks for that catch. Okay, so I'm going to go ahead. I'm going to grab a blue highlighter, and I'm going to highlight the common factors of 12 and 16. Okay, so 1 and 1, those are common factors. 12 and 16 always share a common factor of 1. In fact, any two numbers are going to share that common factor of 1. Now, 2 is also part of this shared list, right? I can see that. And the number 4. Okay, so common factors are 1, 2, and 4. Those are our shared numbers on these two lists. Now, as math people, math thinkers, we tend to do a couple of different things. We tend to kind of step back and go, okay, I have an ordered list. In our case, that ordered list is 1, 2, and 4. What's the smallest number on this list? And what's the largest number on this list? This is a very common math thing to do. If I have a set, to ask what the smallest element in the set is and what the largest element in the set is. And Chloe and I think Ryan have both pointed out 1 is the smallest element and 4 is the largest element. So smallest common factor is 1. Largest common factor is 4. Now, it's kind of more interesting from a mathematical standpoint to ask what the largest common factor is. Do you have an idea of why asking about the largest common factor is more exciting than asking about the smallest common factor? I mean, I could ask either, but the largest one is a little more exciting from a mathematician standpoint. Exactly. So you have the idea of a kind of the largest common factor. I don't necessarily know right away, but I always know what the smallest common factor is, right? The smallest common factor, it's always the number one. So that's not an interesting question to ask. It's a bit more interesting to ask what the largest common factor is because it has a little bit of variance, right? I don't really know what it's going to be unless I do a little bit of work. So that's why we often talk about the largest common factor and not the smallest common factor. And it turns out that the largest common factor has some applications as you kind of work your way through elementary and high school mathematics. That's all. So if something is consistent, it's often not the most exciting thing for math people to talk about. So we don't really care about the smallest common factor, only about the largest common factor. So hopefully that is a nice refresher and hopefully gives you some idea on how you might be able to kind of introduce this topic, right? Talk about what a factor is, talk about what we mean by a common factor. And then you bring up this interesting question of, oh, it seems like the largest common factor varies a little bit. Let's do some more examples on trying to find this largest common factor, right? So that's how I kind of think about it. Is it's an interesting question to ask because I have a set, and I'm curious about what that largest common factor is going to be. Okay, so let's maybe take another. Let's see. Do I want to dive into that yet? Sure, let's do that. So let's find the largest common factor, or greatest common factor, I guess. Oops, I did a bad thing. Let's call this greatest, largest common factor. Can we go back and let's just change this terminology? This is, I'm getting confused with myself with the short forms. I want to call this the greatest common factor. So can you just make that change here? I want to call this the greatest common factor because I think GCF is typically the terminology that's used in textbooks. So I just highlighted in blue the changes we're going to make here. So that means, so this should come out as GCF. So my apologies there. I got a little excited and used the wrong short form, we should be using the GCF short form here, greatest common factor. Yeah, and then lowest, we're going to talk about the least common multiple. Yeah, exactly, which will be the LCM. So there's a GCF, which talks about the greatest common factor, and the LCM, which is the least common multiple or lowest common multiple. Yeah. Okay, so we're going to try to find the greatest common factor of the numbers 270. And should we do one this big? I don't know. I feel like this might be too big. Let's just go with 27. Let's go with 27 and 63, just so you can kind of get another example of making an ordered list and using an ordered list to be able to do some work. We will take a look at how we can utilize factorization to help us too. So with larger numbers, it's really hard to make a list. And it's usually a little bit easier to use the factorization. So what I'd like you to do is when you get down here, we're just going to divide our page up in half. We're going to write out our ordered lists, or our lists on the left-hand side. And what I want to do on the right-hand side is actually use a factor tree. Okay, because kind of the end goal here is to be able to utilize the prime factorization to get at some of these numbers for us when they happen to be bigger numbers. Okay, so first, maybe let's just work on the number 27. And then, I don't know, maybe I could probably put these lists side by side with, I think I have enough room to do that. And I think if I'm lucky, maybe I can get both factor trees in here too. Those are going to ordered lists. So take a few moments to see if you can write down all of the factors of 27 and 63 as pairs. So one thing that maybe you did see from back here is that factors always come as pairs, right? So for something like the number 12, it's going to have an even number of factors. There's something special about the number 16 as to why it only has 5 factors and it doesn't have an even number of factors. I'll let you guys ponder about why the number 16 is a little more special than the number 12. It has a special name, which prevents it from having an even number of factors. Same with the number 1. The number 1 is another one of those kind of special numbers. It has an odd number of factors. Number 4, number 9, these are going to have odd number of factors. They're a set of special numbers. 1, 4, 9, 16, 25. Okay, let's see. I don't think 27 is even. So the next best number we can divide into here is 3. That should give us the number 9. And then I think we're kind of done, right? Can I divide? I can't divide by 4, can't divide by 5, right? So I kind of try like my next numbers. Can I divide by 6? No, because it's not even. Can I divide by 7? Nope. 8, not even. So I'm done, right? So I've tried all of the numbers in between 3 and 9. Nothing else divides evenly into 27. So this is the full list. 27 has 4 factors, 1, 3, 9, and 27. For 63, we have 1 times 63. 63 is not even, so I can't divide by 2. Looks like it's divisible by 3, though. That would be 21. Right, 3 times 21, I think, is 63. Not even, so not divisible by 4. Can't be divided by 5. Can this be divided by 6? I don't think so, because it's not even. So I can't divide by 6. Can I divide this by 7? Can I divide 63 by 7? I think we get 9, right? 7 times 9 is 63. Can't divide by 8 because it's not even. So we're done, right? So, as soon as I've checked 8, I've went from 7 to 8, and now I see 9 over here. So I know that this is the full list. 63 has 6 factors. 1, 3, 7, 9, 21, and 63. Okay, and then we can go through our list and we can find those common factors. So 1 is a common factor, 3 is a common factor, and 9 is a common factor. So we've highlighted our common factors, and then we look for the biggest one. The greatest common factor is equal to the number 9. Okay, so that's how we would tackle that using a list, right? Write out your lists, try to find the largest shared number on those 2 lists. In this case, it happens to be 9. Okay, let's try to connect this concept to the prime factorization. So what I'd like to do first is I'd like to try to break these down using a factor tree so that we can actually write out the prime factorizations. So let's take 3 times 9 for the number 27. And then let's break 9 down into 3 times 3. So the number 27 is actually a really interesting number. It's one of our cubed numbers. It's 3 times 3 times 3. Cool. So this would be the prime factorization for the number 27. Okay, let's take a look at the number 63. 63, let's take kind of like one of our biggest multiplications here. Let's take 7 times 9, right? We know 7 times 9 is 63. And then let's break 9 down into 3 times 3. Okay, so nice, not too bad factor trees here. And let's write out 63 as a product of prime numbers. And I'm going to start with the smallest one. So let's go 3 times 3 times 7. Now, and what I want you to think about, so once you have this copied down, let's think about how does the greatest common factor, where does that show up? Over here. So looking at the prime factorizations, can you spot how we might be able to use the prime factorizations to find the GCF? So that's the question. How could we use the factorizations to find the GCF? Yeah, do you see the number 9 hiding inside of the factorization right here? So the shared prime numbers, when we multiply the shared prime numbers together, we get the GCF. That's interesting. So this is a strategy that we could use for numbers that are bigger and numbers that are going to be relatively challenging to write out a full list for. So if we have the factorizations, we can look at the shared prime numbers and then multiply them. So multiplying shared prime numbers gets us the GCF. And that's important. This is the strategy we use for, larger numbers where it's hard for us to write out a full list of factors. Right? You could imagine if you have like a 3 or 4 digit number, you could have lots of factors, right? You could have like upwards of like 20 to 30 factors. Do you really want to spend time listing all 20 to 30 factors in a list for both of these numbers? Not really. It's kind of annoying. So let's take a look at an example of actually breaking down some of these larger numbers and trying to find the greatest common factor. So let's work on these two large numbers. We have 3,500 and 550. Okay, so maybe divide your page up in half. We'll try to do 3,500 on one side and maybe 550 on the other side. Okay, it doesn't really matter where we start. Maybe let's start with 3,500. Now, it looks like we can divide this evenly into groups of 100. What times 100 is equal to 3,500? I think 35 would work. Yeah, exactly, Chloe. So what I want to try to do, with these larger style numbers is I don't want to necessarily divide by 2, for example. I want to try to find a big even number that I can divide into this. So, looking at the fact that I have 2 zeros at the back end, I know that I can divide by 100. That's just going to speed the process up a little bit. I mean, you could sit here and divide by 2, but you're going to have to do that a few times until you get to a number. And then you're going to end up maybe with like a 3 or 4 digit number, and maybe you won't know where to go, right? So I always kind of recommend trying to divide by a relatively large number first, because now I have the number 35. That's on our 5 times tables, and I have the number 100, which I know is 10 times 10. So I can kind of easily break down the numbers here in the second bit, because I've chosen numbers that are relatively big for that first multiplication. Is it 7 times 5? 7 times 5 is 35, right? So that's pretty much going to finish up the number 35. I can't really break 7 and 5 down any further, but I can break these tens down a little bit further into 2s and 5s. So 2 times 5 and then 2 times 5. Okay, and then 2s and 5s, those are all prime numbers. So that's going to finish up 3,500 for us. And I'm just going to write it as, maybe we'll just try to do this in order. So 2 times 2 times 2 times 5 times 5 times 5. So there's, no, sorry, just 2 copies of 2, my bad. So 2 times 2, 3 copies of 5, 5 times 5 times 5. And the number 7. Okay, so that is 3,500. 2 times 2 times 5 times 5 times 5 times 7. Or 2 squared times 5 cubed times 7, whatever your preference might be. I like it in this kind of more expanded form, because then we can kind of grab the common prime numbers that we're going to have. So I preferred the expanded form personally for the factorizations here. So I'm going to do something similar with 550. I know there's a 0 here at the end. So rather than just dividing by 5, I'll try to divide by 10. Right? I know that 10 times 55 is equal to 550. And then basically now I have stuff that's inside the times tables that I know from elementary school. I know that 55 is 5 times 11, and I know that 10 is 2 times 5, right? So that first breakdown has been severely helpful to kind of break down the subsequent stuff. All of these happen to be prime numbers. So let's write 550. Down here, we have 1 copy of 2. We have 2 copies of 5 and a copy of 11. So those are our factorizations for our 2 numbers. Okay, see if you can find it. What is the GCF of these 2 numbers? $35. Oh, wait, that was an answer to something else. My bad. Let's see, what's shared? So it looks like they share a copy of 2. All right. They also share a couple copies of 5. So the GCF should be multiplying the shared numbers together. So I think it's going to be 25 times 2, right? 2 times 5 times 5. Those are the shared numbers. 2 times 5 times 5. Is that 50? Yeah, so 25 is a common factor. It's just not the biggest one, right? So yeah, so you guys were able to snag a common factor. Definitely 25 is going to be a common factor, but the biggest one is going to be 50. Okay, cool. I'm glad that worked out. How are you guys feeling about that? Do you want to do one more example maybe? I mean, we might as well take it up 4 notches, right? I mean, if you can handle 3 and 4 digit numbers, why don't we just go crazy? So let's try to find the greatest common factor of what number even is this? 69,300 and 4,083,750, just for funsies. If you really want to like have a good time, you can try listing all of the factors of 4,083,750. Please don't. Please don't. There's probably a lot of factors. I'm slightly concerned that these factor trees might be large. So let's maybe not divide. I mean, you guys might have enough room to kind of squeeze the factor trees in, but I probably won't. So I'm going to just do them one at a time. So I'm going to start with 69,300. And obviously I see 2 zeros. So let's divide this sucker into 693 divided by 100, just to kind of get rid of the 100 out of here right away. And that's going to allow us to kind of nicely break down the right-hand side here. So all of this 100 is 10 times 10, and each of these 10s can get broken down into 2 times 5. So that takes care of the 100 bit that is inside of this number. Okay, once you're happy with that, take a step back and think about the number 693. What do we want to divide 693 by? What's a nice number we can divide evenly into that number? 7. Does 7 go in there? That would be fun. 9 definitely does. Right? So remember, you don't have to show this work, but you can kind of mentally check. 6 plus 9 plus 3 is equal to 18. And if we take 1 plus 8, that's equal to 9. So I know that 693 is definitely divisible by 9. And I can kind of do a quick gut check on that. For 7, I'm willing to kind of think about that. 600, I would have to go to my calculator. And yes, it is totally divisible by the number 7. It's just going to take me maybe a little bit more time to grab the calculator and put it in, rather than kind of quickly doing this gut check. I was hoping that someone would say like 3 or 9, because it's very obvious to me that 693 should be divisible by one of those numbers. So I'm going to choose to divide here by 9. You could choose to divide by 7. You would get the number 99. That's totally fine. We should end up getting the same prime numbers at the end. So if we divide by 9, so 693 divided by 9 gives us 77. Ah, I see. So yeah, the 7 is over here. So we're going to get 7 and 11, and then a couple copies of the number 3. So this is what the factor tree will look like if you took the 9 and the 77. If you take 7 and 99, you still should get 7, 11, 3, and 3 as your final prime number. So it doesn't matter how we build this factor tree. There's different ways to build this factor tree, but we should end up with the same prime numbers at the end, right? Because it's a unique factorization. So 69300. It's a really interesting thing. Yeah, it means your students can develop different kinds of factor trees based on how comfortable they are dividing by stuff, right? Or how, which divisibility rules they know or don't know. But that final factorization, so what we write down right now should be the same no matter what our factor tree looks like. Okay, there's 2 copies of 2. It looks like 2 copies of 3. So I have that one, I have that one, I have that one, I have that one. 2 copies of 5. Make sure I don't miss anything by putting little check marks here. A 7 and an 11. Okay, so there's our factorization for 69,300. Now I'm going to leave just a little bit of space here because I'm going to want to put my 4 million blah, blah, blah down here. So 4,083,750. Okay, so I'm going to want to write its factorization up here. So just let me kind of scroll down here and we'll get this one off to a start. Whew, that's a big one. Maybe let's divide by 10 first. Let's just get that factor of 10 out of here. Okay, I mean, when I divide by 10, now I know that I can maybe divide by 25, right? Do you see those last 2 numbers, 7, 5? I know now that I could, divide this by 25, for example, and get something evenly divisible. If you notice that you could just divide by 5, that's fine, right? You can divide by 5 twice. But yeah, I'm going to go with the number 25 here, just because I see that 7, 5 at the back end, right? So I know that 7, 5 should be evenly divisible here by 25. Okay, so dividing by 25, we get still a big number. Oh gosh. Okay, this could it's going to ruin us today. Okay, I know that 25 is 5 times 5. So that kind of finishes off that branch. I guess I could divide by 5 again, right, and see what happens. Right, maybe I'll get a number that's kind of like an obvious multiple of something. So 16, 3, 3, 5. Let's divide by 5. Ooh, okay. So it's getting smaller, which is good. So 3,267. Okay, I know 5 is prime, so I'm going to circle 5. I don't know if 3,267 is prime. My guess is probably no. Let's see, can we add up those digits? So this is what I'm going to want to kind of think about first. What if I take these digits, 3 plus 2 plus 6 plus 7, and I get 5, 11. Ooh, that's good. So if I add up these digits, I eventually end up getting the number 9. So that means either this number is divisible by 3, maybe you would have guessed that, or this number is going to be divisible by 9. So I'm going to take the number 9 and see what I get. So 3, 2, 6, 7. Let's divide by 9. I get 363. Ooh, I'm feeling good now. I'm feeling great because I know that 363 is divisible by 11 by the sandwich rule. Okay, 9 is not prime. Let's break that up into 3 times 3. So that branch is done. And then, like I said, I know that 363 is divisible by 11 because the middle number is the sum of the 2 outside numbers. I don't know if you guys remember that. If not, you're going to take a look at 363. You're going to take these 2. You're going to add them together to get 3 plus 3. And then you're going to look at the other number, which is 6. And these 2 numbers are the same. Okay, so since those 2 numbers are the same, we know that this is divisible by 11. That's kind of a long way to do it with a 3-digit number. And let's say, is this 33? 363 divided by 11 is 33. Cool. Okay, if you didn't see that it was divisible by 11, you could try dividing this by 3. 3 plus 6 plus 3 eventually will get us to 3, 6, or 9. So it is going to be divisible by 3 again. And then you'll eventually get 121, right? And hopefully you'll realize that's 11 times 11. So either way we go, we should get a couple copies of 11 and a copy of the number 3. Ooh, okay. I have to zoom out here for this tree. So we got a lot of different factors. I'm going to be putting just little check marks underneath the red circled numbers just to make sure that I get them all in the factorization up top, okay? So let's look for the number 2. We have 1 copy of 2. We have 1, 2, 3 copies of 3. 1, 2, 3. Lots of 5s. 1, 2, 3, 4 copies of 5. 1, 2, 3, 4. And no 7s, and we have 2 copies of 11. Okay, so I think that's all of the factors. 1, 2, 3 3s, 4 5s, and an 11. Yeah, sweet, that should work. Okay, so just up here, I'm going to put like a little therefore, 3 dots. So therefore, the GCF is what? What is the GCF? Take a few moments to multiply those shared numbers together. Let's see, I'm going to go ahead and I'm going to start finding some of the shared stuff. So that's shared. We have 2 shared copies of 3. We have a couple shared copies of 5 by the looks of it, and a shared copy of 11. Okay, I don't really want to try to do this in my brain. I probably could. Oh man, I kind of want to, but I'm not going to. Okay, so 2 times 3 times 3 times 5 times 5 times 11. So I get 4,950. That's a pretty big common factor. That's a big common factor. So there you go. There's a relatively, I would say, a relatively big example of finding a common factor. How do you guys feel about that process? Does that feel okay? Yeah, you got it. So you multiply all of the shared prime numbers, right? So when I look at the factorization, if they share a prime number, I want to add that as a factor of the GCF. Yeah, exactly. So that's why you kind of see me in the past examples, I've kind of tried to highlight, right? So when I look at these two numbers, there's a shared copy of 2 and 2 shared copies of 5. So I take 2 times 5 times 5. Down here, we had a shared copy of 2, 2 copies of 3, 2 copies of 5, and an 11. So I got to multiply all those together to get the GCF. Yeah. Just be careful that you don't duplicate. That's all. Greatest common divisor is used sometimes as well. I think the GCD used to be an older kind of term, or it's a term more used, I think, in computer programming than GCF. Most of the updated textbooks, I think, use GCF from what I've read. But yeah, they could use GCD as well. Yeah, they mean the same thing. And it also depends on your online resources too, right? Your online resources may call it the GCD. I'm trying to be consistent with our notes. So when we talked about multiplication statements, we basically called those two things factors, which is why I want to use GCF. So I want to make that explicit connection that the greatest common factor is a factor of this large number, right? It's one of those smaller numbers that we've multiplied together to get this large number. So, if I wanted to, I could take 4,950 and I should be able to divide evenly into both of these bigger numbers, right? I should be able to divide my GCF into 69,300 and into this 4 million number as well and get an even output, right? An even divisibility. Okay, let's just quickly define a couple of new things, and then we'll end class a little bit early today because I have a phone call I do need to make, and that'll give us some time if you have any kind of final questions as well. Let's talk about multiples and common multiples. Okay, a multiple is any number that we get by doing skip counting by a number. So this is why skip counting is important, because it defines our times tables, right, or our multiplication facts. And a multiple is any number that lands inside of the times table, inside of our set of multiplication facts. So let's say we wanted to skip count by 3. We get 3, 6, 9, 12, 15, 18, and so on. All of these numbers are called multiples of 3. Okay, another way to think about it is if I can take a number and divide by 3, the starting number is a multiple of 3. Okay, so all of these numbers share the property that we can divide 3 evenly into them. Okay, so that's another way to think about multiples. If you can divide evenly by the number that you're working with, it's going to be a multiple of that number. Okay, so that's just a little refresher on what we mean by multiple. And then we want to talk about what does a common multiple mean. So for a common multiple, we kind of want to set it up like a common factor. We would like to have two numbers that we're working with. We want to kind of look at the list. And then we want to find the numbers that are shared on these lists. Okay, so we're going to take two numbers. We're calling them n and m here, but for the purpose of doing examples, these will be actual numbers. We're going to write out the list of multiples for these numbers, maybe by skip counting or maybe by you knowing your multiplication facts. And then we're going to take a look at the shared numbers on these lists. And any shared numbers we call common multiples. So as an example, let's work with, let's say, the number 4 and 5. Okay, we're going to start writing out the numbers we get by skip counting by 4 and the numbers we get by skip counting by 5. I don't know about you, but I tend to skip count by 5 a little bit more often. This one's a little bit easier for me to do right away. So 5, 10, 15, and 20 this is a nice pattern, right? And we're going to go all the way up to maybe like 45s, 25, 30, 35, 40, 45. And then the list, of course, can keep going. So I'm just going to write that out with a couple of dots here. I could keep going if I needed to get more multiples of 5, but going up to 45 is going to be enough for the purpose of this particular example. Okay, skip counting by 4 is a bit harder. So maybe you'll have to remember your multiplication facts for 4. So 2 times 4, 3 times 4, 4 times 4, etc. Okay, and we're going to go up to the number 44. And then if I needed to extend this list, I could, but this will be big enough for the purpose of the example we're working with. Okay, and then what we do is we kind of go back through these lists that we have, and we take a look to see if there are any shared numbers on these lists. Do you guys see any shared numbers on the list for 4 and list for 5? Yeah, 40 is a shared number. Yep, so 40. And yep, 20 is a shared number, right? So 40 is a shared number and 20 is a shared number. Of the numbers we've written down, what do you think the next shared number would be? 60. Yeah, exactly. So once you kind of notice the shared numbers and notice the pattern's always going to be consistent. So the pattern's going up by 20. The next shared number is 60. The next shared number is 80. So that pattern will continue for our common multiples. Okay, so let's write that down. So let's write down our common multiples. And I'm just going to put dots here just to denote that there are more, right? We could make more if we wanted to. Maybe let's write down the next couple multiples just so that we have them. Okay, and then being the math nerds that we are, we're going to ask a couple questions. We have a set of numbers that come in an order. We're going to ask what's the biggest and what's the smallest inside of this set, right? So what is the greatest common multiple? And what is the least or the lowest common multiple? What's the lowest common multiple? What's the smallest number on this list of common multiples? It's 20, right? Yeah. Okay, this is different from our factors, right? Our lowest or least common factor was always 1. That was an uninteresting question to ask. So it's different. We can actually have a lowest common multiple that looks like it's going to vary based on our starting two numbers. That's interesting. So the least common multiple is an interesting question to ask. What about the greatest common multiple? What's the biggest common multiple that we can make for 4 and 5? I mean, 80 is the one on the list. But yeah, there's dots here, right? Like this keeps going. On the list that's written, it's 80. But this pattern keeps going on infinitely. It goes on forever in that rightwards direction. So we can't really determine the greatest common multiple because the list just keeps going. Right? So we would say that the greatest common multiple, it actually doesn't exist because this list keeps going forever and ever in that rightwards direction. So hopefully that makes sense as to why we don't ask the question about the greatest common multiple. It doesn't make sense to ask that because it doesn't really exist. But the lowest common multiple or the least common multiple is an interesting question to ask. And that's going to be kind of what we're going to look at a little bit on Wednesday. Cool. So if you have any kind of last minute questions and or concerns, I will field those now. Otherwise, just remember that by Wednesday, that video assignment is due. It's due at midnight though. So if you have any kind of final concerns about the video assignment, you can let me know Wednesday. You are very welcome, guys. No worries, no worries. Have a lovely rest of your day. And yeah, I'll kind of keep working away at, so if you haven't gotten your feedback yet, I'll keep working away at marking for you guys as well.